Hello everyone, this is Mrs. Lindsay. Today we're going to talk about implicit differentiation section 2. Okay, so we have considered a lot of functions this semester and finding the derivative of it. And we've seen notation, specifically more that we've used here on the left in terms of finding the derivative and in function notation. We have used this somewhat over here on the right, but not as much as the other two. So we're going to expand on this just a little bit more today. Okay, so what does this notation mean? So this means that we're finding the derivative of y with respect to x. Okay, so the derivative of y with respect to x. Right here a little bit, and let's do an example here. When we find the derivative, f of x equals 2x raised to the fourth plus 3x. So I'd like to go ahead and pause the video, do this, and then check your answer when you're done. And again, we're probably using this notation here that you're a little more familiar with. Again, go ahead and pause. Okay, so you can go ahead and check your answer here. And then notice again that this is solved for y, and that's typically the problems that we've been finding the derivative of when they're already solved for y. But what do we do if they are not solved for y? Okay, so an example of that would be something like you're seeing here. Okay, so in order to do this, we're going to use something called implicit differentiation. Okay, so we're going to be using this notation, dy dx. Okay, derivative of y with respect to x. All this means is that we're finding the derivative with respect to x, where x is the independent variable. Okay, because sometimes solving these problems, we might not be able to isolate y, or it's not very practical to do so. So again, we can actually use what we call implicitly finding the derivative. And what we're simply using is the chain rule. Okay, so a couple steps for this. And if you need to, please pause the video and write this down. For steps for implicit differentiation. So we're going to differentiate both sides with respect to x. Okay, careful with the chain rule here. Then we're going to collect the terms with dy dx on one side, factor out dy dx, and solve for dy dx. Again, please pause this if you need to write this down. But let's go ahead and do a few problems here where we want to differentiate with each expression with respect to x. So in the first case here, we have 4x to the third, so we're just going to do the power rule. So 4 times 3, 12 times x squared. And then I'm going to go down here to b. Now this one does not have x in it, it has y in it. So we're essentially doing the chain rule. So we would still do our power rule, 2 times 3, so 6 of that something raised to the first power. So we still leave that something raised to the first power, but now we have to do the derivative of y. Well, the derivative of y is dy dx. Derivative of y with respect to x. Okay, so again, we're implicitly doing differentiation, differentiating, but again, it's essentially just really the chain rule. So if you go up here to so again, we're going to find the derivative of x, which is simply just 1. Now we're finding the derivative of 5y. Well, the derivative of that is just 5. But again, we're doing the chain rule of derivative of y. So that's dy dx. D, so here we have the product rule. We have x times the derivative of y to the third. So we have times 3y to the second. Derivative of y is dy dx. Plus the second times derivative of the first. Derivative of x is just simply 1. So again, we can simplify that a little bit, but that essentially is what we're doing with these. Let's take a look at some other examples. And this one's a little bit more similar to the first example that I did a couple slides ago. So here we have the equation x cubed plus y to the third equals 4. I summarized over here in the right-hand corner, let me move this up a little bit. The steps we would take that was on the previous slide to actually differentiate here. Okay, so the very first thing that we're going to do is we're going to differentiate both sides with respect to x. So we're going to differentiate x cubed, so that's going to be 3x squared. Plus, now differentiate y to the third. So again, bring the 3 down of the inside squared. Well, the inside is your y, so that's dy dx equals, find the derivative of 4, simply 0. So we've done the first step. We also want to now write all the terms with dy dx on the left side, or isolate on any side, actually. So I'm going to subtract over a 3x squared. Factor out dy dx. In this case, it already truly is. We only have the single term over there, so we've really done step 3. And then we're going to divide to solve for dy dx. So I'm going to divide by the 3y squared. So dy dx equals negative 3x squared divided by 3y squared. And we'll simplify that. So we'll get negative x squared divided by y squared. Okay, so let's try another one. Put these up a little bit. So same idea here. In this case, x squared plus y squared minus 2y minus 4x equals 4. We're going to differentiate both sides with respect to x. So 2x plus, again, now we're essentially just applying the chain rule here. So 2y, and the derivative of y is dy dx. Minus 2, and the derivative of y, again, is dy dx. Minus derivative of 4x, 4, equals derivative of 4, which is 0. Again, we differentiated both sides with respect to x. Step 2, write the results of dy dx on the left side. So again, isolate these terms right here. So I'm going to subtract 2x, and I'm going to add 4. That. Factor out dy dx, again, so this is like a GCF in both of these terms, so I can simply, again, factor those out. So I'm left with 2y minus 2 in parentheses there. Factored out dy dx. Now we're going to divide by 2y minus 2 on both sides. So dy dx equals 4 minus 2x divided by 2y minus 2. And we can factor out a 2 out of all of those. So again, we can reduce that all by 2. So 2 minus x over y minus 1. Okay. Another example here. Find the slope of the graph x squared minus 9y squared equals 16 at 0.51. Okay, so I would like you to right now, we'll address finding the slope, but I would like you to take the derivative of this equation with respect to x. I would like you to pause the video, do that first, and then check it, and then we'll discuss finding the slope at this 0.51 once you have done that. So please pause the video, try that, and check it. Okay, so here's the derivative with respect to x. Okay, so let's talk about this just a little bit. To find the slope of the graph of an equation at a single point, we used to do, this used to be solved for y. We would take the derivative and then we would substitute in x equals 5 to find our slope. Again, derivative is the slope at any point at a tangent line along the graph. Well, in this case here, now that we've found derivative with respect to x, we can simply substitute in the ordered pair 5, 1. So in other words, x for 5 and 1 for y. So here we will get our derivative, our slope, 5 over 9. So either approach works, but again, it's sometimes much more practical to use implicit differentiation to find the slope. And you know the order pair 5, 1. Okay. And let's try another example here. Find the derivative using implicit differentiation at the point -1, 4. So in other words, we're taking the derivative here with respect to x. Okay, that's what this notation is referring to there. So again, I would like you to try this one on your own. Please pause the video. Find the derivative with respect to x, and then find the slope at the point -1, 4. Okay, so let's go ahead and check your answer here. I do want to point out a couple things here when we are taking the derivative here with respect to x. So the derivative of 2x is 2. However, we need to use the product rule here. So the derivative of the, so we have the first times the derivative of the second. So x, derivative of y is 1 dy, plus the second, which is y, times derivative of x, which is 1. Then we took the derivative of y with respect to x, which would just simply be 1 dy dx. Derivative of 6 is 0. So then at that point in time, I distribute through the negative, isolated dy dx, then factored out the dy dx to find my derivative with respect to x as y minus 2 over the quantity minus x plus 1. Then at that point in time, we're going to substitute in -1 for x, 4 for y, to find our slope of +1. Okay. So this is our first day of implicit differentiation. We'll do a little bit more tomorrow. However, here's your homework. And that concludes section 2.7.